All right, guys. So let's get started with our usual review of all last week's labs, right? So we looked at principal component, which is pretty neat. Let me start with the labs real quick. So here, what's my lab? Okay, that's what it has. Let me go to Colab. Oh, all right. Sorry, guys. Give me 1 second to upload the notebook here. Give me 1 second, guys. Let me get the classrooms. All right, that's what I'm looking for. All right. Somehow Google's not pulling it from here. I'm just going to download it and install it. Excuse me, guys, 1 second. All right. Sorry about that. I thought I can import directly from Google. GitHub, I mean. All right, give me 1 moment. I'll get this going. So how did you guys do in the labs? Let me see here, right, in our class folder. All right, good. I see. I'm always happy to see good submissions. So why don't I start with one of your submissions, right? So Janine, let me see. Actually, yeah, Jalal, you can see, you can look at yours. Oh, cool. All right, very good. So this is looking good. I'll just make a copy just in case. All right, guys. So I'm looking at PCA, right? So what's the idea for PCA is, we talked about this, reducing dimensions, right? Meaning creating a new vectors to represent the old vectors, but in a reduced dimension space. So that's why, right? So here, what we are doing is we are going to actually, right? So here in our usual imports, right? Here's our data. Let me clear all the outputs so I can go line by line. Okay. So here's our data set we are importing, right? So it's a cost data you guys probably seen for k-means. So idea here is it's just like a very simple PCA. So the idea here is, can you reduce the number of dimensions, right? So, and one of the classic use case of PCA is graphing data, right? High dimensional data, because obviously, in the graphs you can do you can do 2 dimension very easily, maybe 3 dimensional, but beyond that we cannot visualize it, right? So what if you have like 10, 20 dimensions? How do you kind of reduce them into, right, small dimensions so at least you can visualize something, right? And that's what this lab is about. All right. So basically, we are dropping the model, right? So we just have the numbers, right? And that's why, because to do PCA, we need to have numbers. And that's another reason I like the data set, because it's all numbers. Okay. Now to do PCA before, we need to scale. So again, you guys know all this, right? We have done all this before. So we are doing a standard scaler to scale it down. So you can see that, how the data changes, right? So MBG is 0, right? Now it's 0.15. So again, and as you can see, right, we are kind of, and this is where, machine learning, when you sort of build on small steps, when you do like a good project, you will bring in a lot of the skills you learned, right? So for example, if I say, all right, code and scale, right? Now you guys know how to do it, because you have some sample code, you can copy paste and very easily get going. So that's why, and I'm really glad we sort of built up, this, little segments of skills. Right? All right, we got the data frame scale. Very good. So another option you can do, kind of like, I'm just showing you both options. So here you can do standard scaler, right? Or you can just use a built-in pandas version, right? Data set, So so if you look at the formula, what am I doing? So if there's a formula, kind of like where you would imagine it's like, so x minus, right, mean x, mean of the data, right? And then I'm dividing this by standard deviation. That's basically the idea. But when you apply this to pandas, right, it'll do it for all the numbers, which is pretty cool, right? So if you sort of compare, the numbers should be more or less the same, right? I mean, there should be some variation because this is floating point math, right? But for the ballpark, right, here's minus 57, right, 58. So it shouldn't be like a huge variation, right? That's what I'm trying to tell you guys. So either one is fine. Right? All right, so very good. So this is actual PCA, right? So everything we have done so far is data manipulation, right? Bringing data to a format. So again, so here's my PCA importing, right? And here we are using 2 components, okay? And that's it, fit transform, right? What am I transforming? Scale data. Now remember, and one thing you will notice is I'm not doing training, testing split, none of that. Why? This is unsupervised. So there's no separate separate test. It's like we give the entire data to PCA and then say, yeah, just show me 2 components. Okay. All right. There we go. Now the components you get back, so PC1, PC2, right? They have no resemblance to the actual data, right? I mean, if you try to figure out, okay, where is this 0.65? If you try to sort of find 0.65 here, you wouldn't. Remember, because it's like you have to remember the making a fruit juice or smoothie example, right? You're putting all the fruits in, you're hitting the blend button, and what you get is like a fruit juice. So you're going to get a mix of everything, right? And that's what you see. So since, why am I getting PC1 and PC2? Principal component 1, principal component 2, and that's an MV given, right? Which is pretty good, because we're looking for 2 components. Let's say you want 3 components, just change it to 3. That's it. So, all right. So now I want to kind of plot these components. So here we are plotting PC1 and PC2, right? Because my original data was high dimensional, right? Like what, 8 or 10 columns. So I kind of reduce them into kind of 2-dimensional and trying to figure out if there's like something we can pick up, right? I'm not seeing like a big like clustering, like like big aha moment here, but it is something, right? And in some data sets you will see the data will cluster very well together, right? But here it's fine, right? It's what it is. So right, I get the scarce data. Is that going to make sense, guys? Right? All right. So the next thing I ask you to do a correlation matrix. All right. So this is the original correlation matrix. Remember, correlation between -1 and +1, right? And then one second. Yeah, let me see a question here. Yeah. Okay. Yeah. So I will explain what the correlation is. Yeah. So this is the original data, right? Even though scale data, the correlation matrix is pretty similar, right? So you can, again, we know how to read correlation matrix. Diagonals are 1, 1, 1, 1, 1, right? Everything on 1, and then between -1 and +1. For example, let's say if you look at the MPG row right here. Okay, so which one has biggest correlation? For example, I look at MPG and cylinder. That's pretty interesting, right? So more cylinders you have, right? So cylinders have a negative impact on MPG, right? So -0.85. So that's on the other end. Remember, it's -1 and +1, right? So it's kind of, and we know this, right? I mean, the bigger the engine, the less the mileage, right? So cylinders increase, you can see MPG kind of decreases, right? I think this is the engine size, like like a 1.5 liters, 1.6 liter. So again, same thing, right? It has the same negative impact on my MPG, like larger the engine, the more mileage. horsepower, same thing, right? And let's see if I find it positive. Interesting. Again, so I need to go look at what these are, right? But so these like it seems like like VS has a little positive impact. AM is automatic transmission, whether yes or no, right? And then that seems to have positive impact. So correlation matrix is pretty good because we can sort of get a sense of how these guys interplay. All right, that's great. Now what I'm asking you to do is like find the correlation for the PCA data. All right. So as I remember, we only had 2 components, right? So so diagonals is 1, so that's good. But what about the everything else? It's 0. Does that make sense to you guys? Right? That basically means these vectors are nothing like. They have no interaction whatsoever. Does it make sense at all? What do you guys think? Why am I getting zero correlation for PCA?
They are orthogonal.
That's right, right? Exactly. Remember, the whole point of PCA is, right, if you remember this, right? Let me bring up the slide here. All right. When you draw your PCA axis, how do we do? Right. So if we draw a first axis and we draw a second axis, they have no overlap. Right? They are completely orthogonal to each other. So I mean, this is in 2 dimension we can visualize, right? But imagine even as a multi-dimension vector, these vectors are orthogonal. Why? Because we do not want any overlap between these guys, because we don't want the vectors to kind of be like this. Then they're kind of capturing each other's data, right? So there's no use. I want the vectors to be like this, right? Completely orthogonal, right? Because that's the idea, right? Because this vector is capturing everything along the axis. So I want the next guy to go and capture, whatever this guy missed, right? So orthogonal. Right? So that makes sense, right? So and then our PCA confirms that. So yeah, right. So these vectors have nothing in common. That's exactly what we like them to be. Pretty cool, huh? So just going to confirm, yes, our PCA worked. And this is some other, right? When you have PCA, right, you can sort of print out some of the metrics, right? And for example, remember, we went from 11 columns original, right? And then we went to PCA, we reduced them to 2, all right? And then what we have done is, and you can sort of see here, right? So each PCA component is composed of 11 elements. Why is that? Because if you think about this, remember, so, and here's the first PCA component is made up of 11 components. Why? So think of your smoothie example, right? You put all these fruits in the blender, you put your bananas, you put your strawberries, right? And then you hit the blend button. Whatever comes out is a mixture of everything, right? So yeah, so each PCA component, and you see the ratio is different, right? So for example, this guy is made up of right, and these are what we call the coefficients. So you can go back, right? You should know what's the equation used for to derive a PCA component, right? Because we have access to the model. But when I give the PCA data to somebody else, where was that, right? They have no idea what the original data is. For them, it's just like, okay, I have 2 columns, A and B. That's it. Okay, very good. So that's why, right? So original data is 11. So even though so each PCA component is made up of 11, right? 11 components. Very good. And ratio, right? So what are the ratio they're explaining? So remember, when we think about each component is going to capture some part of the data, right? So the first one will always capture the most part. First principal component will capture the most part, right? So the 60%, right? The second one only captures 25%. And as you're going to keep going, like for example, let's say you create 3 PCAs, right? The next one will be even less than this, and so on and so forth. But combining these two, right? So combining these two, right? 60 and 24, if you combine these two, you can have 84% coverage. So just by using 2 components, right, you have 85% coverage from the original data. That's not bad at all, right? So that's how you have to think about this, right? And the next one is I asked you guys to do 3. So again, same thing, right? PCA, new PCA with n components 3. There we go, right? That's it. All right. And Let's do it. Okay, interesting. Yeah, let's see how this graph looks. I don't know if you have Plotly installed in Google. Oh, cool. Very nice, right? So it's like a little right? And by the way, I don't know how many people have used Plotly before. Plotly is kind of an interactive, very web-friendly graph, right? So you can actually interact. You can actually even zoom in, right? So again, right? So you can see it has like a little controls, right? You can zoom in, like use your mouse to zoom in, zoom out. Pretty nice. Yeah. Okay. That's very good, Jalal. I'm really glad you did this. Yeah. So, all right. And then you can sort of move over, measure the points. Very cool. Very nicely done. Yep. So cool, huh? So, and then so this is a 3D plot because you can do 3D in Matplotlib as well, but it's a little cumbersome, right? But Plotly is does pretty well. And also, let's look at the correlation matrix for the 3 component, right? So here's our 3 component. So let me do, if we do correlation matrix. Okay. So what do you expect to see? You expect to see zeros across. There we go, right? So diagonals are 1, everything else 0, right? PC1, right? You can see everything is 0, as they should be. But yeah, so that's pretty cool. Yeah. So even though I randomly picked Jalal's notebook today, I'm glad I did because I really love to see them Plotly, right? So these are the things we all kind of learn from, right? Because it's like once you see the data, like, oh, this is pretty cool. This is something you want to adapt for your own graphs. Pretty good, very good work, Jalal. Yeah, very nice work. All right, guys, any questions on this one? So basically what we have done is we did a very simple PCA, right, for the sole purpose of just kind of exploring the algorithm. And basically we just did a plot, right? That's it. So my sole was like reducing PCA into like small dimension, so I can do a plot. So first we did 2D, and then yeah, I'm really happy to see the 3D plot as well. Perfect. And if you think this is like, oh, this is like kind of made up example, I'll tell you it's not, right? So take a look at this one. I was inputting. So let me put this link here for you guys. So I was teaching a machine learning class this week to CVS, and this is something we went through. Look at the chat window, guys, in Zoom. All right. So what we have, so this is NLP. So one of the things about NLP is, just to give you a little context, you have a bunch of text. When you analyze the text, you're trying to figure out, right, what's the relationship between the text, like with the words. So basically what we do is we convert the text into vectors, right? And then once we have the vectors, we can project the vectors into a vector space, right? And then we can actually visualize them. Let me show you guys. So is everybody on this page, guys? Project@tensorflow.org, right? So here the model I'm looking at is called word2vec 10,000. So it's 10,000 words, right? And the actual vector dimension, so imagine like a spreadsheet, right? So I have 10,000 rows, and then 200. So vector space 200, meaning it has 200 columns. So number of columns is 200. So your vector, can I imagine this, right? Imagine you have a vector. Let me bring this up. So let's say you have a word, say hello, right? So I'm mapping into a vector. So let's say this becomes like, so let's say if we're doing like a 2-dimensional vector, something like this, right? 0.42, right, minus 0.1. So this is a 2-dimensional vector, right? Now if we keep adding to this, right, then if I add another component, right, 3-dimensional, right? So what I'm doing is I'm converting a word into a bunch of vectors. So word2vec, right, actually is 200 dimensions. So word2vec is actually in 200, so now we are 200 dimension vector, right? So that's what we are loading. So you can see, right, word2vec, if you click on this one, you see word2vec 200,000, 200, right? And there are different models, you see like, like, for example, MNIST image, they have, we have 784 columns and so on and so forth. Anyway, right? So let's look at this one. So I have a 200 dimension vector. So imagine like, right? So imagine you have an array of, 200 numbers. How do we visualize this? And what they are doing is, right, they're actually doing PCA. You sort of see this at the bottom here. They are doing a PCA analysis. So they are breaking them. they're bringing it down to 3 PCA components: PC1, PC2, PC3. And then they're doing it. So I mean, this graph is the same thing, right? It's like a 3D graph, right? You can sort of, right? You can sort of move around, see it. And each of these dots, we move your mouse around, move your mouse over these dots. These are words. You see that? Yeah. And it'll sort of, take a little animation. That's pretty cool. Now, what if I want just a 2D graph? I would say, you know what? Just show me, component 1 and component 2, right? So, I can turn off component 3. You can see here, right? So I'm not doing z-axis anymore. So now, just a 2D graph. All right. So they are doing, and they already done some PCA, so you can sort of select the component you want. You want to select the first 2 components, right? Because they capture most of the data. So x-axis, I'm showing PCA1. Y-axis, I'm doing PCA2, right? And the z-axis I just turned off, right? So now my graph is just 2-dimensional, right? So this is not, so this is not like a made up example. This we use this quite a bit in the industry, like basically visualizing data. And let's say now I like 3-dimensional. Turn it on, right? And then right. So now you can sort of see the axis. I see the green axis, right? Red and the blue. Right? These are that's how they are kind of visualized in 3 dimensions. All right. So how does it useful? So you can move your mouse over. You can see the words. That's fine, right? Also, you can zoom in, right? You can use your mouse, like so, use your mouse pointer to zoom in, right? And the idea here is you can see the proximity of the vectors. Let me sort of zoom into some, an area that's not as crowded, right? And let me sort of zoom in here, right? Let's say I see like these 3 guys. So look at this word. This guy, laureate, right? Cricketer, right? Footballer. So maybe like professions, right? So the words are kind of clustering together. Football, right? Hockey. That's pretty cool, right? So you can sort of see, I see like a little cluster here with a bunch of words, like football. So footballer and cricketer kind of playing side by side. Makes sense, right? Because these are athletes, or professional sports, right? And then here's hockey, here's football, right? Pianist, wrestler. Right? So by looking at these words, you guys can see, yeah, right? This is right? This is pretty cool, right? Coach. These are kind of this area kind of represents people's profession. Let's go to some other area, right? So for example, over here, right? Here's like animated, piano, right? Baby, right? So you can sort of say cartoon, right? So say animation and cartoon, right? Kind of like this, so right? So you guys can see this is how we can visualize the word relationships. And then you can pick in a random, right? Pick like some random cluster, right? So how things are, right? So yeah. I think these are musician's name: Andy, musician Johnny, right? Really, right? These guys, pretty good. So Chuck, right? Chuck Berry, Anyway, so every area you zoom in, they will kind of have the way the algorithm captures the data. It will kind of cluster similar words together. Pretty cool, right? So again, just PCA, right? The way we are able to visualize this is by using PCA. And you can sort of search for a word. So for example, you can search for the word, say music. All right. So, and then so then you pick a word, say music, right? And then they're going to show you the similar, words that are close to each other. So when you look at music, musical is a word that's very close. Jazz, dance, right? Art, rock. Anyway, you guys get the idea, right? So these are all pretty similar words if you look at this. So let's say you want to choose a word, say, I don't know, exciting. Maybe not that then. Exciting. Happy, let's say. All right. So that's the word happy, right? So these are the words, you can sort of see the word distribution, right? Where the words are located. And you can see, right? Words that are close to with happy. Let's say, I don't know, funny, right? So you can see the funny is like, humorous, crazy, right? Joke. And you can see how the, right? You can sort of see how the words are distributed. Anyway, so this is a pretty nice application of PCA, right? Because I was kind of explaining this to them, and then I kind of thought, oh yeah, I should show this to you guys today, right? This is basically PCA in being able to visualize words. Pretty cool, right? So any question on this one, guys? Does it make sense? All right. So, sorry, David, where do you see the question? So total variance 8.5. Where do you see that? Oh, right here. Okay, yeah. So what's happening is, like, like they're kind of capturing. Look at the PC component one. It's only capturing 3.8, right? Second one is capturing only 2.5, right? Third component is capturing only 2.2. So we add them all up, right? Capture 8.8, 8.5. Yeah. The reason these guys are not doing, like, remember, in our example, right? Wait a second. In our example, right, we actually got, the first PCA component captured how much? 60-something%, right? If you remember this, here we go, right? The reason it's not doing it here, we are seeing, like, very small capture. This is basically, this is a hugely dimensional data, right? So that's why, even when you do PCA, you're unable to capture. So not all the data will, like, come to, get, sorry, will be reduced efficiently. So yeah, again, simply add them up, right? Component 1, 2, 3. We can add them up. Why? Because they are orthogonal. Yeah. Yeah. Good, guys. So makes sense. Yeah. So so Word2Vec, this is whole another, right? Another algorithm. I'll just show you guys very quickly. So the idea behind Word2Vec, right? So let me, I'll just bring this up because this is what I was. I'll just show the screen right here, right? So this is a class I was teaching yesterday. All right, so you guys been doing machine learning for the last few months. Algorithms want vectors, numbers, right? So we call them vectors. But what if you have a bunch of documents? So your data, we just did, like, for example, if you look at the car data, luckily for us, it's all numbers. So we can easily fit into machine learning algorithms, and they can do the math. But what if I had bunch of words? So algorithm cannot handle words. So the first step I had to do is then I turn the words into vectors, right? And then you can apply your algorithm. Then you can apply your your classifiers like SVM or anything we want, naive Bayes, anything we want. But the first step is vectorizing, right? So when you vectorize words, right, we want to be smart about this. We want to smart, like, and typically when you do vectorization, like, they kind of, they don't. We want to capture the meaning as well. Like, for example, let me show you guys this. Right. So for example, when I'm just vectorizing words, right, I also want to get the meaning. For example, let's say I have words apple and banana. In the vector space, I want apple and banana to be close together, right, because they're fruits. And they have cats and dogs, right? We want them to be together because this way we know, right? And that's what you see in the embedding projector, right? Because it actually, if you sort of zoom in, right, and zoom into a cluster, right? Let me sort of reset, right? If we zoom into a cluster, right, and then sort of try to sort of see, look at the similar words, right, and and right. So for example, right, right, Muslims, minority, right. So so the idea idea here is, say, communities and governments. Anyway, so it's kind of fun to kind of look at these, look at some of this clustering, and the way it's picking up this clustering is reading the text and figuring out how the texts are positioned. Like, looks at how the texts are, like, written, right? So it'll just read like Wikipedia and all the text, and then it'll pick out how the words are being used, right? For example, I see a word like communist, for example, right? So there's a word communist, right? Most likely, you wouldn't have word communist, and the word banana next to each other, right? Because they don't happen in sentences. So maybe you say something like, maybe like a communist country, right? Or communist, regime, or some communist government, right? And that's why the word development says, oh yeah, so word communist and the government kind of happens, side by side. So I'm going to sort of put them together. That's what it is, right? Is that going to make sense, guys? Yeah. So that's the basic idea for the algorithm. So our interest here is, and again, the Word2Vec is a pretty complex algorithm, but at least you get the idea, right? It extracts meaning. Our interest was, understanding the PCA component part of it, right? So when you have large dimensional vectors like these guys, right, this is 200 dimensions. We had reduced them down into 3 components to visualize them. Okay, good, very good, guys. All right, let me do the next one real quick. So I'll just use, Jalal, next notebook as well. Don't mind. It's the PCA2. Okay, yeah. All right. So the first one was basically, just to kind of, so we get the idea for the how to use PCA, right? So this one, right? This one is basically, hopefully it looks complete. So let me copy. All right. All right. So, and this is like, so again, some, wine quality data. So you sort of see, right, what we're getting into, right? So this is the data. So, it's just bunch of measurements of your wine properties, right? How much acidity, what's your pH, and all this. So good thing is it's all numbers, right? So we don't have to do a lot of encoding anything. All right. So the idea is we're trying to figure out the quality, right? This is sort of what we are trying to figure out. So let's say you're on a wine tasting, school or something, or right, club or something, and you're trying to basically assign score to your wines, right? The thing is, when you do PCA, doesn't matter because you're like PCA just looks at the entire data, and the whole thing is just going to distill down to fewer dimension, right? So, all right, so we are dropping quality. All right, there you go. So we are down to like 12 columns, okay, and all numbers, right? Again, we don't, like I said, if we sort of look at the wines, makes sense, but right, just imagine it's just a bunch of columns with numbers, right? All right, so vectorize, okay, correlation. So let's do the correlation properties here, right? So, yeah, right. So what I'm saying is, right. So again, this is the original data. You can see, right. For example, what's the correlation between, say, pH and something else, right? For example, you can see that, of course, right. The more more acidity they have, right, more positive the pH is going to be, right? Anyway, so you can sort of look at the data. All right, so normalizing. So you're using the just a pandas normalizing technique. All right, got that. So everything's normalized. So PCA, I'm saying, okay, right, how many PCA do you want? So here we are doing 7. Okay. So again, you can sort of see here numpc is 7, right? And basically we are transforming the feature vector. So let me show you guys this. Right. So we basically, so I know you had 5 too, so let me just do 5 real quick, right? Just to kind of illustrate the point, right? So we're reducing like 11 columns into 5 PCs, okay? And you can see, right, PCs are completely different. There's no like, there's no, you cannot find the similar number. They will look exact, completely different than the original data, right? All right. So correlation matrix, again, you will see, right? Diagonals are 1, everything is 0, exactly the way we want. Okay. Again, so here's like some, some basic information. So we can say, right, with 5 components, right, you can sort of, you're printing out the how much variance they're capturing. So the first one captures 28%, second one captures 17%, and you'll see like keep decreasing, right? So remember we have 5 components. So basically total cumulative, right? Basically, we add them all up, right? So how much are we capturing? Almost 79%, right? Using 5 components, we're able to capture 79% of the variance of the original data. That's not bad at all, right? So to the plot, right? So here's kind of the idea, right? Idea is basically, remember, we have each principal component, 1, 2, 3, we have 5, right? So remember, first one captures 28%. So we're starting at 28% here, right? And then the next one captures how much? 17%. But we're adding them up, right? That's the idea, right? So we are kind of, we keep adding them up. So you can sort of see here, if we only use two components, you kind of have about like maybe like what, like 45% coverage, right? And if you go to 3 components, we are about 60%, I would say, right? So, and then, you guys get the idea, right? So they can, the reason we can accumulate them because they're completely orthogonal. There's no overlap, right? That's why. So, and then finally say, oh yeah, with 5 components, I'm almost close to 80% coverage. Pretty neat, right? So, and this is called spree graph, right? So, and then let me see, right? Okay, yeah, and then these are like right. For example, kind of what are the features are being used. So this is pretty cool, right? So each component, right? We are using, right? How is PC1 computed? Oh, that's pretty cool. I'm really glad you did this one. Yeah, that's very good, right? And because remember, these are like remember, these are all blend of original data, and this is this is a mixture of original data. You can sort of see here, right? Pretty neat. I really like this one. Good work. Yeah. Let me see. Let's see what the graph looks like. Oh, plot.show, I think, right? Yeah. Oh, actually, yeah, you're doing the next one. I'm sorry. Yeah, such a function. Yeah. Oh, cool. Yeah. So, so this is a kind of, sometimes it can be a little hard to kind of, explain, right? So the way we are doing this, right? So typically when you do access, we'll do X and Y, right? But here my X and Y is my first access is PC1, right? Remember, right? Principal component 1 and then principal component 2. And then we are kind of seeing, right, how these data points are mapping in our new axis, right? Because what PCA does is, right, it gives you like a whole new set of axes, right? Like this. So imagine you're kind of plotting these in X and Y axis. And basically what this graph is showing you is how everything else is kind of mapping into this. Does that make sense, guys? Right? Yeah. So you can see, like, for example, right, like citric acid, right? So if you look at the, this is a 0 point, right? 0 point is here, middle point is 0, 0. You can see sort of, pH is kind of stretching more on this side, right? It's going negative on the PC1 side, right? And it has very little influence on PC2. Why? Because if you measure this pH, right, PC2 is very minimal, right? So let me see if I can confirm this here on the top, right? There we go, right? See, when computing, PC1, pH is very influential, right? And you see it here, right? And then PC1 axis, pH1 is really extending its influence, right? Let's look at something in PC2. So which attribute do you guys think is more influential on PC2 axis? Kind of you're looking at this way, right? Which one is kind of which one is larger vector, right? So let the what is it, total sulfur dioxide? Okay, yeah. Let me see here, PC2, right? See, that's a dominant feature. So basically, sulfur dioxide, right? Total sulfur dioxide is the first dominant feature. Next one is free sulfur dioxide. Right? And if you look at the graph, it makes sense, right? Because these are the large vectors influencing PC2, right? And something like residual sugar, for example, is kind of in between, right? It's kind of so right, it's kind of it's kind of going this way, and it's kind of like doing like a midpoint. So I'm sure you will see residual sugar being used, right? There we go, used here, right? Used here, and actually when you look at PC1 and 2, right? So, right, you will see it used. I mean, if you sort of went further, you will see it, right? So kind of makes sense, guys. So kind of how to sort of right? We are looking at data in a different axis. Yeah. Okay. Very good. Yeah, very good graph. So yeah. Good, guys. Any other question on this one? Let me see any question in the chat. So I'm looking at the question. I'm guessing what you're asking is, the way you're thinking about PC is, remember, you're completely changing how the data is represented, right? The original data is like 11 dimensional, right? You have 11 columns. But when you do PCA, we've switched them to 5 columns, right? So completely separate, right? So now you have basically new axis, right? So the 11 columns are reduced into 5 columns. And remember, even with 5 columns, I only have about 80% coverage, right? I don't have 100% coverage, and that's a part of PCA, right? When you reduce dimension, you're essentially going to lose data. So imagine you are compressing a photo, right? So you will never see the original representation when you compress it. The idea is to keep as much of the original data, but with much smaller size. So you're definitely going to lose some data. You will never get 100% coverage. But if let's say, for example, you're happy with 80% coverage, that's good, right? You can just get by with 5 components. And imagine, right? I mean, this will come into play when you're like hundreds of dimension. And let's say you want to reduce it down to maybe 10 dimensions, right? It'll save you a lot of time, compute time when during training. That's the idea, right? So you have to think like you're kind of creating a completely new axis, right, to represent data, not the traditional X and Y axis, right? So that's what you think about this. Very good, guys. Very good notebook. Very well done, Jalal. Yeah, really like the details and the way the code is segmented. So very nice. Good work. Any other question on this one, guys?
Can you hear me? After one hot encoding, I got this error.
Good deal.
Too many values to unpack.
Any other question on
any
labs or PCA? concept-wise? Excellent. All right.
Oh, can
so,
you hear me?
And yeah, so again, I'll share the notebook with you guys. So yeah, and this is why I like. So this, I'm really happy to sort of see good quality submission. So that's very good. Excellent, guys. So let's go to the next recommendations. Right. So we sort of look at the algorithm summary. Right. Kind of where we are. Right. Okay. All right, so remove
can you hear me,
machine learning algorithms, right? So we just did the last algorithm is PCA, right? Not supervised. Again, there are a lot of other algorithms. So we are kind of covering the important ones, right? And the last one here in our list is recommendations. Right? So there we go, right? So we are pretty much at the end of the algorithms, right? So
can you hear me?
let me look at this recommendation. So this week we're going to do a recommendation lab, right? And so I'm a little behind updating the reading materials, guys. Sorry, apologies, because it's been just a busy week with no time. But I will get them out to you guys, right? Because I want to make sure the links I send you guys are quality links, right? So I can review the links, watch the videos before I write them in the guide. So, but the idea here is, and that's why I'm sort of spending time going over the materials here, so you have some basic understanding, and then when you go to the labs, right, you actually put it in practice. That's the idea. So I hope that works for you guys, right? But yeah, but I'll have the reading materials completed by next week or so. All right, let me see questions. Sorry, I'm not getting your voice, guys. 1 second. Can you guys hear me okay though? But I'm not hearing your. Give me 1 second. Let me kind of connect to Zoom again.
Can you hear me?
I hear you fine.
Yeah.
All right, now I can hear you. Sorry. Okay, yeah. Before I wasn't. So go ahead, Vasilios. Yeah. So I'm just hearing you now.
After one quote encoding, I got this strange error. Expected 2 values, and I can't find an answer for that anywhere.
So where are you doing the one-hot encoding?
It was a list of words and then became 0, 1.
Okay.
And one-hot encoding. So
okay.
I did use the PCA and I got that error. I can't find the answer, so I couldn't proceed.
Gotcha. Do you have this notebook here? I can take a look at.
No, I didn't upload it because it was useless for me. I didn't want to give a useless one.
Right. Okay. So again, we can take a look at the code, but basically when you get this error, usually that means do you have a lot of zeros in the data, something like that, right? Or like a lot of NAs.
I think it is expected, yes.
Yeah.
So encoding, yes.
Right. So double check that. Double check if you have a lot of NA values, right? Like empty values, right? Because sometimes I've seen this happening. I'll share the notebook with us, and we can take a look. Yeah, I think could be the data is missing. A lot of data is missing, so one hot is failing, right? All right, guys.
Well,
all right, so now I can hear you guys. Sorry, before I wasn't. So anybody else have any questions? So yeah, so go ahead and upload the notebook, and you can share with the group, and then we can take a look, right? Yeah. Anybody else have questions, guys? Right. So I just realized I couldn't hear you, but now I can. Okay, so let's zip through recommendations real quick, and this is really interesting. And then I'll set up the lab for you guys. This is a really fun part, and I think this is a nice way to kind of finish up all the algorithms. So this week we are going to work on recommendations, but we should also start thinking about a final project. Right, that's going to be the following week. So you guys have done like your algorithms on very different kinds of data. So what you want to now, and I want your input on this one, guys, too, right? I want this to be the final project to be useful. So let's start thinking about what do we want as a final project, and how we want to do this, right? Because I want this to be involved, use real world data, bring in at least a few algorithms, right? You know what I mean? Just, kind of an end-to-end project. So thinking about this a little bit, and let's talk more next week. But then we won't have any coverage. But start thinking about this, please, right? Because this is your final capstone project, and I want to make sure, and I'm going to have everybody choose their own data, right? But we should set some basic criteria, like what we want to see, right? Because I want whatever you guys are doing, I like you guys to sort of publish on, say, GitHub, and this should be something you can of good quality that you can showcase on your resume, right? It should be that it should be like some little trivial thing, right? You know what I mean? Like it has to be something really solid, so that you can say, yes, this is my machine learning project. Doesn't have to be one thing. You can do like a series of part 1, part 2 kind of a thing, right? So definitely plan on publishing on GitHub if you can, and even better, if you can write like a little little blog post, right? You can do it on GitHub right there, right? GitHub, you can publish a blog, or you can just write on like Medium or something, right? So yeah, just to kind of just because and the reason I say this is it'll compel you to find a good solid project, right? Because now you're going to write about this, what I mean, something public. So is that going to make sense, guys? What I'm aiming for? So you can choose any data set, you can use multiple data sets, right? But it'll be better if they're going to build on one another, right? So you make it, let's say you want to do like a 2-part series. So part 1, maybe you can cover the basics, and part 2 you can do something else. But it'll be like, rather than 2 like different projects, it'll be nice if they can sort of build on each other. Yeah. So start kind of thinking about this, because I'm sure when you guys are doing your own algorithm, you guys encounter data set, you're like, oh, that looks interesting. I want to go look at the data, right? So anybody has any ideas? Can I just very quickly, just any thoughts? On some some of the data sets you guys have seen, some of the examples you guys have seen.
Could we pick something that's on the Kaggle?
Yes, absolutely. Yeah, you can pick a Kaggle competition, exactly. Yeah, and then you can pick one of from the past competitions, exactly. Yeah, that's a great because Kaggle you use competitions of there's some pretty good real world data, right? And then that needs like some significant processing and exploring before you can do machine learning. Yeah, I think that's perfect. That's a good place to look. Yeah.
Thank you.
That's very good. So right, so kind of so I'll tell you a story why, just to give you a little context, and then so we just said COVID data set, absolutely, right? So that that's very timely. You can definitely do this. So whenever I work for a company, we hire machine learning, like data science, machine learning interns, right? So when you interview people, sometimes they will say, yeah, I've done this in school, right? I've done machine learning in school, and they will know the basic algorithms. But the people we really end up hiring were the people actually, I think we had 3 people. They actually went out their own way, and then they created their own projects, machine learning projects, and they had GitHub code we can look at. And they also kind of written about like what they have done, what's their process, right? Step 1, I did this, and why did I do this kind of thing, right? With the code and everything, because it really forces them to be a higher quality, right? Because you're going to post it publicly, maybe your employer will see that, so you don't want to like just like something, some simple thing, right? And the people we end up hiring, even though they haven't had any practical experience, these are people actually not just say, oh, I did machine learning, right? I did a machine learning course. They actually went and did a machine learning project. So if you're trying to make like a career change, and like to get into machine learning, this is how you do it, right? Because when we interview people, we know, right? A lot of people learn machine learning like as a hobby. Maybe that's not part of the main job, but so they never had a chance to use machine learning at work. But so how do you prove you actually have good knowledge, right? Not just theoretical knowledge. This is how, right? You showcase a project that we're going to look at and say, oh yeah, this is pretty decent, right? I'm pretty impressed the way this person has done it. So think about it does with that level, right? So is that going to make sense, guys? What we are aiming for? Yeah. So yeah, the question was, yeah, if you're going to use COVID, there are tons of COVID data, right? So again, when you choose the data, right? So one thing your aim is like, when you do machine learning on the data, it has to give you like a pretty good conclusion. You know what I mean? What I'm saying is like, there should be an aha moment at the end, So and you know that's kind of hard to define. Like, but you know it when you see it. It's like, you know, let's say someone you did like a COVID machine learning, and then you said, oh, you know, I discovered like this relationship between this and this. And when I do machine learning, I can predict, you know what I mean? Like, you know, there has to be something at the end, you know. So just basic, you know, doing like a basic plots and things like this, and that's fine. That's a prerequisite. You understand the data, but your machine learning has to yield something that is not obvious, the original data, right? I mean, making sense? So maybe you can say, oh, okay, COVID, you know, I figured out the colder the climate, I'm just making this up, right? The higher the infections, right? And you know, here's how we discovered that, right? And here's like a little graph that explains it, right? You got to kind of, you know, think on that level. Yeah. So yeah, that's why I'm mentioning it now, guys. So you know, you have like a couple of weeks to think about. We'll talk more detail next week, right? After we complete our algorithms, and then next week onward we'll start the project. So I kind of want to allocate maybe 2-3 weeks, right, for the project, and then so that'll probably take us into the holidays. Just so take some time off, and maybe like the first 1 or 2 weeks of January, we'll kind of do like a project presentation and review, and then we'll wrap it up officially. That's what I'm thinking. Yeah. What are you guys thinking? Hey, again, you know, you can think about this for a while, and you know, we can talk more. But you know, if you have any thoughts, we can share right now. Right. So, yeah. So, like I said, good quality, right? so yeah. So, because yeah. Imagine you are going to, you know, show this to employer, future employer. Yeah. All right, guys. So let me think on you guys on this one, but let me show a recommendation real quick. And this is going to be our last lab, like a last structured lab, right? Next one's going to be project. All right. Let me start here. Okay, I want to make sure. Okay, good. All right. Recommendations, right? So understanding recommendations. You know, we see recommendations everywhere, right? Whether we, you know, buy on Amazon or Netflix, right? Recommendations are very, very important. So this is Amazon Prime recommended video. When you look at the recommendation, what do you guys think? Is it a good recommendation? What do you think is going on with this recommendation? Yeah. No. Okay. Kim says yeah. No. Why
This
not?
only suggests that same device might be used by multiple people, adult and kids.
That's right. Yeah. So you know, my kids use my account to watch, you know, their cartoons and whatever, right? And you know, I have my thing. So what they're doing is, since you know they're kind of looking at it as one account, they're recommending for like you know, right, based on everything I'm watching, right? So there's no like a clear segmentation. How did, for example, Netflix solve this problem? Right? I'm sure you know we're all watching Netflix, a lot of Netflix these days. How is Netflix solving the problem?
They look at the genre and the words that does match, which goes along with that, with the kind of an index.
Yeah.
And then they search through that index and then say what would be the next weighted hit that can come across.
That's true. Yeah. So that's one approach. How do they solve the problem of like multiple people using the same account? Right, you know, right in a household, you know, everyone using the same Netflix account, right? How do they? And then everyone has a different taste profile. Exactly, right. So yeah. So have you seen this? Like, you know, when you launch Netflix, you will see like, you know, they'll say who's watching, right? They will ask you like, okay, you know, who's watching Netflix, and then you select a profile, right? So in our home we have, you know, so we have 4 profiles, right? Me, wife, and then my 2 kids. And they all have their own thing. So so we have 4 profiles in our Netflix, right? And then the recommendation is not an account based, but profile based, which is much more accurate, right? Because everybody kind of watches their own thing. Anyway, so right. So the reason I showed you guys this is like recommendations. You have to be careful, like you know, I mean, algorithm is one thing, but sort of how you sort of collect and curate the data is another thing, right? You got to kind of, you know, right? There are a lot of things you have to think about. Okay. So recommendations are very, very important. For example, right? In Netflix, 2/3 of the movies people are watching are recommended, which is pretty true. I mean, you know, I do this all the time, right? When I watch something and Netflix come back and say, oh, you know, since you watched that, we are recommending this to you. Right? Sure. So I'll click and then I'll like it, right? Amazon. 30% of the sales are recommended sales. I mean, that's a lot of money, you can imagine, right? So it's like, I mean, imagine, and I know this, firsthand, right? Now I do a lot of Amazon shopping, and when they recommend, say, oh yeah, hey, do this, that's it, right? We end up buying it. So these are, so recommend is not like something you just want to, it's like a nice to have. It's like a must have, right? Amazon is a lot of revenue. Netflix is a lot of, views, right? So it's very important to do high quality recommendations. Yeah? So now, how do they do recommendation, right? So for example, you can do a few items. For example, you can recommend based on the past behavior, right? For example, if you're Netflix, you rated a bunch of movies, right? Based on your ratings, they can recommend things, right? What if you don't have any, you haven't rated any movies, right? Then how can they recommend? So maybe they can use something else. Maybe they can use, maybe like they can say, your age, for example, right? So maybe like, if you're 20 something, maybe, from all the other, 20 something subscribers, they can know, okay, hey, these are the movies they liked. So even if you don't have any ratings, they may recommend movies that other 20 somethings liked, right? In Amazon, same thing, right? Let's say in Amazon, I don't write any reviews on Amazon, right? But how are they recommending? What they're doing is they're looking at the purchase pattern. They're saying, okay, if, in Amazon, how they say, when you buy something, they'll come back and say, oh, people who bought these items also bought this item, right? So they're not going by reviews, like, you don't write a review yet, right? You're just buying items. So what they're doing is they're doing item matching. Remember, this is the clustering problem we talked about in K-means, right? That they're clustering shopping baskets. So if I have items like A, B, C in my shopping basket, they're going to go and say, okay, hey, people who had A, B, C in the shopping basket also had D, right? So clustering, right? So you can sort of see how everything's kind of coming together, right? So there are more than one way to recommendation. So we're going to look at one solid way, which is basically something called collaborative filtering, right? So again, the process goes like this, right? So imagine in Netflix, I have users, I have movies, right? So let's say I have ratings for the movies. Then we actually train our model, right? And once the model is trained, then right, we recommend movies from that. Same process as supervised learning, right? So we're training first, and then we do the prediction. Yeah? The reason context matters is like, remember, like for example, let's say my model predict these are the top 5 movies for you, right? But let's say you already watched movie 1 and movie 2. So I don't want to recommend movie 1 and movie 2 to you because you already watched them, right? And you'll be annoyed if the same old movies kind of keep showing up on your feed, right? So that's where context matters, right? So so not just what the model says, but also we want to sort of analyze, process what the model says with whatever context we have. For example, maybe user has already seen this movie, right? So we don't want to show it again, right? Things like that. So, all right. So let me show you guys a couple of examples. So this is pretty cool. It's called Netflix price competition, right? So Netflix did this competition is about 10 years ago. Yeah, not 10 years, almost, yeah, 10 years ago. So basically they released a bunch of ratings, right? They released about 100 million ratings by about 408,000 users, right? And about 18K movies. So there's a lot of data, right? And then, so what they did is like, they basically released this format: user, movie, and rate. That's it. So you can imagine like a little Excel spreadsheet, right? User ID, movie, and the rating, like 3 stars, 4 stars, 5 stars, right? Whatever the rating was. And so the idea was, they said, okay, if you can improve our algorithm by 10%, you win $1 million, right? So the winning algorithm actually improved the algorithm by exactly 10%, and 10.06%, right? Just enough to win the prize, right? So that's a pretty good competition. Let me show you guys the leaderboard on this one, all right? So this is a leaderboard, right? So those are the two, so the top 2, right? So the 2 teams managed to solve the problem, right? They basically improve the algorithm 10%, right? But 1 is the winner. Why is that? Can you guys look at the data and tell me why Belco won this? What do you guys say?
Timing. The time that you submitted.
That's right. Look at the submission time. Exactly, right? So same day, 2009, 7 July 26, that's the date, exact same date, exact same hour, 1800, 6 p.m., right? Only apart by what, like 20 minutes, It's so they exactly the same thing. You look at the numbers, right? They're the exact identical, but just because one team submitted 20 minutes before, they won the $1 million. Right? I mean that has to hurt, right? I mean if you miss out $1 million because let's say you want to get some coffee before submitting, right? And then you come back and right, you lost the competition. Right? Yeah, that has to hurt. Anyhow, so the idea is, right, this competition was pretty powerful, but through real world data. You can still download the data, right? The data is still available on Kaggle. So, right. So kind of after the competition is done, they did an analysis and they basically published a paper. They said, so the idea for them is basically they said it's extremely simple to produce pretty decent recommendations. Right? I mean, when you do a lab, you will see, right? It just takes like maybe 10 lines of code to do this. However, it's extremely hard to improve them, right? So recommendation algorithms are pretty good now. You can just spend like maybe half an hour to come up with a recommendation algorithm that is pretty decent. But it's going to take you like lots and lots of work to improve your algorithm after that. So one of the studies they publish is like, so this is like this is algorithm performance. This is, remember, they are calculating root mean square, Rmse, right? So Rmse is between the rating algorithm predicts and what the actual rating is, right? So remember in Netflix, in the old version of Netflix at least, right? When they recommend a movie, they will say, we think you will give this movie 4 stars, right? But let's say I ended up giving 3 stars. So that's a delta, right? So that's a, right? Since this is a regression problem, right? Because we are doing ratings. And Netflix says, okay, then the delta is 1, 4 minus 1, right? And then, when we did a regression, remember we talked about Rmse, root mean square, as a way of calculating how accurate my algorithm is, right? So it's basically what the algorithm predicted, like what my rating would be and what my actual rating is, right? So the idea is if they match, algorithm predicted correctly. But if they differ, then there's like some error, right? So we ideally want an Rmse to be 0. Right? If my algorithm says I'll give this movie 4 stars or 5 stars, and I should be giving it 4 stars or 5 stars. If I don't, that's an error, right? So in an ideal algorithm, perfect algorithm, you'll have Rmse 0, no error, right? So, but again, this is hard to achieve, right? So Cinematch, so this is the Netflix algorithm. So this is the Netflix algorithm, right? They actually had before the competition, right? So the Rmse is kind of pretty close to 1, right? And the price, right? Remember the goal is what? Improve the algorithm by 10% at least, right? So Rmse reduced by 10%. So this is the price. So this is Netflix algorithm Cinemax. This is the price. So remember, Rmse improved by 10%, right? Let's say you're another video company. You're doing like simple average predictions, right? Just like a run-of-the-mill average prediction. You can see these are pretty close, right? Right. I mean, average prediction is look at the Rmse, right? They're very close to each other. Maybe like 0.5. Right? That's not a whole lot of difference. If you do random recommendation, right? For example, let's say you look on Netflix and they're randomly just giving you movies, right? And that that has a high setup because why, right? Rmse is pretty high because I'm not using any logic at all. I'm just doing it randomly, right? So random is Rmse. So, but if you look at the sort of the common approaches, if you just look at a simple average algorithm, that is pretty good Rmse. Netflix, this is Netflix, right? And then this is the price. So you can see they are pretty close together. And this is why the statement that's people say extremely simple to produce decent recommendations, but extremely hard to improve them. Yeah. So anyway, so I know. So you just need to understand the context, right? Yeah. Interesting. Okay. So I see your link. Interesting. Okay. Yeah. Good. All right, guys. So let's look at one algorithm we are going to use. It's called collaborative filtering. It's a kind of a pretty classic algorithm, but it works really well. All right. So let me show you an example. Very easy algorithm to learn. So let's say this is my ratings matrix, right? Let's say I have users in rows, right? User 1, user 2, user 3, and they have items. Let's say these could be movies, this could be shopping items, whatever we have, right? And these are the ratings, right? 4 stars, 5 stars, 3 stars. Okay. So look at the item ranking matrix, right? So first question for you guys: is this going to be a sparse matrix or dense matrix? What do you guys think?
It's a sparse now.
Yeah, it's a very sparse matrix, right? Because imagine Netflix, let's take an example Netflix, right? Let's say Netflix, they have, I don't know, like say 100 million users maybe, right? So you're gonna have 100 million rows, right? And let's say, I don't know, they have like maybe, say 100,000 movies maybe, like 100,000 movies. So I now have a matrix of, 100 million times 100,000. But how many of the cells are actually populated? Very few, right? Can I look at your Netflix behavior, right? I mean, do you rate every movie you see? Most likely not. Right? We made like here a few movies here and there. I mean, usually people rate the movies they really like or they really hate, right? If you're kind of neutral, you're like, oh yeah, that's fine. I watch a movie that's decent. Moving on to the next one, right? But if you really love the movie, you'll make sure you rate it. But if you really hate the movie, same thing, you'll rate it, right? Because that's how we know. That's our psychology, right? So a lot of the cells in this matrix are going to be blank. So this is a hugely sparse matrix for us to try to solve. And it can be a pretty massive matrix too, right? So you can imagine this matrix can be pretty massive. So we cannot solve the matrix as it is, right? We need to come up with some other approach. But let's say for the time being, let's say we have the matrix. And I'm asking you a question. So look at the ratings, right? Look at the ratings given by each user. I want you guys to find a user that closely matches the taste profile of user 5. So look at the one highlighted, right? So I want to do some recommendation for user 5. And the task for you guys is to find other users that have a similar taste profile. What do you guys think? Which user is pretty close to user 5? U1, right? Because you can look at the ratings, yes, it seems like they have the similar rating, like, 4 stars, 4 stars, 3 stars, 3 stars, right? So now if I'm recommending a movie, since I said, okay, hey, user 5 and user 1, they seem to have a similar taste profile. So since, user 5 rated this movie pretty high, right? I can recommend this movie, right, to user 4, user 5. Right? Because, they have similar taste profile, the ratings are pretty close to each other. So, so I can take a bet, whatever this user, rates pretty high, also user 5 will like it as well, right? So we recommend the movies. This is the basic idea of collaborative filtering, right? We'll compare the ratings. We see, we find similar taste. We do this. But now we're sort of eyeballing, we are comparing the ratings manually, so we are fine, right? How do we do this programmatically, right? And for this, right, we have this thing called, let me show you guys this, cosine similarity. So let me show you guys this, right? So imagine, right, you've already seen this, right? It's in the same matrix, we're comparing user 1 and user 5. What if, right? So the way you look at the cosine similarity is like this. We plot the data onto axis, right? So for example, let me show you guys this. There we go, right? So let's say I have users and movies. And when I plot the data, let's say I have 2 movies, movie 1 and movie 2. It's just 2-dimensional, right? We plot the ratings. Okay. So user 1, movie 1, he gets 4 stars, so 4 here. And then movie 2 is 3 stars, right? So the coordinate is 4 and 3 right here. Then user number 2, right? 4 stars for this movie and then 5 stars for the next movie, right? So again, imagine I'm putting dots on, into the axis, right? Now, let's say they are very close together, right? And how do you measure this? Remember, these are vectors. So how do you measure this? We measure the angle between the vectors. So imagine you're kind of drawing, like, this is 2-dimensional, right? Now we can easily kind of, measure the angle, right? So if the angles are kind of wide apart, right, then they have nothing in common. But the angles are pretty similar, then they are pretty good, pretty similar tastes. Is that gonna make sense, guys? Visualize, right? Yeah. So what we measure is we measure the angle between these vectors. And this is called cosine similarity, right? So, and this, remember, this is just 2-dimensional, like movie 1 and movie 2. What if I add movie 3? Now we have 3 axes, right? Movie 1 in this axis, movie 2 in this axis, movie 3 in this axis. Now my vectors are 3-dimensional. But the angle, the equations is still the same, right? Right? Even though we cannot visualize them all that much, right? It doesn't matter how many dimensions we add. So you can have multi-dimensional vectors, and we just measure the angle, like how close they are. If they're overlapping, same taste profile. If they're kind of different, if they're orthogonal, then there's no match, right? Remember, when it comes to the PCA, right? Vectors are orthogonal. There's like they have nothing in common, right? So the same idea. It's called cosine similarity. that make sense, guys? Right. So this is the one we are measuring to figure out what how these users are similar taste. Yeah. So now the complexity, as you can imagine, is going to come from, right? Let's go back here. The size of the matrix, right? So look at the, right? So first of all, we have sparse data, right? So from the Netflix price data, right? So you can imagine this matrix, right? There are 500,000 users, 15,000 movies, right? Basically, it has like, if you do the multiplication, there's like, 8.5 billion cells, right? That's a cross-sectional cell, right? But only out of the 8.5 billion, only 100 million actually had data. The rest were like zeros. So you have this huge sparse matrix, only few cells have any value, right? And you can sort of see here, right? Right? Kind of just doing the basic math, right? If you have 100 million users and 100,000 titles, so do the math, right? And right, how much data that is. So this matrix will not fit on a single machine, the matrix as it is. So we need to be a little creative on how to solve this matrix, right? And the way that it's done is basically using matrix factorization, right? I'll just show you guys the basic idea, right? The idea here is, let's say you have one massive matrix, right? How do you solve the matrix, right? And the algorithm that we use is basically kind of use ALS. It's calling all netting least squares. So we're not going to go to the math side of this. I'll just give you a high-level explanation. So it's kind of doing like a right, sort of a dimension reduction, right? Basically, you have a massive matrix. How do you sort of condense the matrix into a format that we can actually solve the matrix, right? Right. And this is done by factorization. So this is like a pretty pretty classic technique that's used. So the idea here is this. Let's say I have one massive matrix, right? This is the users and items. And we know this is very sparse and very, very big. So what we do is we sort of factorize the matrix into two smaller matrices, right? The idea here is these matrices are basically much denser, right? The sparsity is kind of compressed, right? The dense matrix. However, these are not exact representations. So using these two matrices, right? The one I created, when you sort of process them back, I can get almost back to the original matrix, not 100%. Maybe I'm losing some data, right? So just like when I did the PCA, right? When I put them back, right? I don't get to 100%. Same thing here, right? I'm losing some definition of the data, but I can pretty approximately get back to the original data. That's why it's called approximation, right? Not exact. Because if it's exact match, then these has to be pretty large as well. So if you're kind of compressing the matrix to a much more manageable form, the goal is not to lose too much information. So using these two matrices, you can still get back to the original matrix, not the 100%, but pretty close to 100%. Does that make sense, guys? This is the basic idea behind factorization, right? Why are we doing this? Because this matrix in its original form is pretty impossible to process, right? Because it's pretty large and pretty sparse, right? So what we are solving is we are breaking into two different matrices, approximately, right? Anyway, that's the idea basically behind this, right? And then, so once you kind of break them into matrix, then we can do SVD, singular value composition. Again, these are basically matrix operations, right? So if you kind of curious about the details, pick up any textbook, they will explain how to do SVD, right? But SVD is basically using it, it's computationally very intensive. So the approximation is ALS, right? So remember, we had two matrices, right? From the original matrix, we sort of created two matrices, U and V, right? And how do you solve this? So SVD is one option, but it takes a lot of compute power. So the approximation, we use the ALS algorithm, right? So basically, ALS kind of does an approximate solving, and you can tweak the knob to sort of how close you want to get to the original, right? So the more close you want to get to the original matrix, the more compute time it will take, right? So for example, and also ALS, one of the cool thing is it's easily parallelizable. And that's why a lot of the recommendation system use ALS, because for example, something like Spark, right? Spark has a built-in ALS algorithm, because why? Spark runs on multiple machines, right? So imagine you have kind of like this, imagine like this, right? Imagine you have a bunch of machines, your data is spread across many machines, right? Let's say you have some matrix here, right? Since ALS is independent, when you do the matrix multi-processing is independent, so you can basically sort of do your processing in parallel on multiple machines without having a lot of independence. Right? So that's why. So that's why it's called parallelized. It's very important. Right? Anyhow, so ALS algorithm is pretty easy, computationally efficient, and right, and then it will solve those two matrices, right, to get the original value back. Yeah. Oh, question is why cosine? Yeah, that's a great question. So the similarity between vectors, right? We talked about cosine similarity, right? It's basically this gives you an accurate answer of how similar the vectors are, right? So yeah, so I know, so because tan is basically a function of cosine and sine, right? So we use cosine. So cosine similarity ranges from between 0 and 1. So you get like a pretty, right? So it's normalized. So that's why we prefer cosine similarity. Right? Yeah. So again, we can come up with, and that's not the only vector measurement. There are a lot of other measurements, but this is most popular because it's easy to compute, very fast to compute, and also pretty accurate, turns out to be, right? So that's why. Yeah, exactly. So you can sort of look at, or when you do some textbooks, you can ask, how do we find similar vectors? So you will find lots of other methods. Yeah, cosine is just one of the popular ones. Exactly. Yeah, thank you. Yeah, good question. Yeah. All right. So we got it, right? So we understand the idea for ALS, right? So when you do our labs, right, it's basically you are using ALS algorithm behind the scene. Okay. Let me see if I can bring this up here. I'll upload the lab for you guys to start the labs, right? So let me see. And don't worry, I will actually upload this to you guys in the reading material. So recommendations, right? So recommendation, we have 2 labs. One of them is called Movie Lens. So Movie Lens is basically a data, as you can imagine, right? Movies and ratings, right? So the data looks kind of like this. Let me see an example. Okay, let me show you guys the data. So data kind of looks like this. So I have, imagine like I have a spreadsheet, user ID, right? Movie ID and rating, right? And user could be, let's say user 1, right? Movie 1, and the rating is, let's say 3.5. So we are doing scale of 0 to 5, right? And the same user 1 might rate in another movie 2, maybe he gave it like 5.0. So user 2, maybe another movie, same movie 2 did like 4.7 or something. You know what I mean? You guys get the idea, right? So this is the matrix looks like this. So think like an Excel spreadsheet, users and movie ratings, right? So based on this, we are going to do the computation and we are going to understand what the data looks like. Yeah. Yeah. All right, guys. So let me do a quick demo, and then you guys will solve this on your own as well. Right. By the way, we are using a package called Sparse, right, to solve this problem. Right. So the reason we use Sparse is they implement some of these common matrix algorithms. Right. It's very easy to do recommendation with Sparse. Right. So, and if you look at this again, I will review this next week. You'll get like a starter kit, right? So basically, you can see, right? You're loading, right? Movie runs like 100,000 ratings, right? And then we are doing the training. Why? Because we want to basically the algorithm to learn how the users rate the movies, right? And then so training is pretty quick. You can sort of see here, and so this is using ALS, and also this is using KNN as a baseline. Remember? So remember you look at KNN, nearest neighbors, right? Because the ratings are close to each other, so you can say, yeah, that they are similar profile, right? So it's a fast algorithm. That's why they are using it. And then what are we measuring? We are measuring Rmse, right? Because remember, this is a regression problem, right? Because you have basically the idea is, can the algorithm predict pretty close to your original rating, right? So we are treating them as just numbers. And then, yeah, we're trying to predict, how much is, so for example, let's say this is algorithm rating, right? And let's say the algorithm thinks, I will give this movie, let's say, 3.0. Then the delta, you guys know all this, right? Then the delta is basically, or the residual is basically, right? Is the actual minus, right? 3.5 minus 3. Right, 0.5. Anyway, you get the idea, right? So this is all, we covered in the regression algorithms, right? Just basically mention the delta. So you want to get as close to the original rating as possible, right? So that's the idea. All right. Anyway, so here, right, you can, what do you can see? Fold. Now we know what this means, right? They are doing cross validation, right? And each cross validation, right? They're printing out, okay, what's the Rmse they are saying? Because Rmse is that, you remember root mean square error. This is the one they're trying to minimize, right? We want to see as close to 0 as possible, right? But if you look at this, they're pretty much around like 90, like, right? 90, it's like 0.9, right? So, and then they're kind of saying, how much time it took to, actually train the data, right? All that stuff. So anyway, so I'm doing a cross because, I'm doing a systematic search of the space, right? And then basically, you sort of, find the, right? You get the data set and then you predict. So my average Rmse is about 0.55, right? Anyway, so and what you will find is, right? What I'm doing is, these are the movies, right? So for each movie, right? So, you see the movie ideas. So let's say you like this movie Toy Story, right? And what I'm doing is, okay, let's say you like this movie Toy Story. What other movies you would like, right? And the algorithm kind of comes back and say, yeah, so, these are the movies we're recommending. So Get Shorty, Usual Suspects, yada, 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 right? So what you will do is, like, you can change the movie name, right? Let's say you say, I like, whatever, right? Something monsters, some movie, and the algorithm will go and basically, what is it doing? Just doing a lookup, right? It's looking at the nearest neighbors, right? To look up the algorithm to say which movies you will like. So again, you're gonna imagine this like vector space in them. These movies are kind of dot, in like points. If you like one movie, you want to kind of find the one that's kind of closest to the, the movie you're looking for, all right? So anyway, so and you can see these are pretty, pretty good recommendation, right? If you like, say, right? If you like Get Shorty, you will look, this is the movies you will like. Anyway, you can play around with this one. It's a really fun data set, and that's recommendation, right? We're using Sparse. So as you can see, we're not doing any matrix computations here. Why? It's all done by Sparse package, right? That's why we like Sparse, because we don't want to go low level and do like the matrix operations, right? So it's all done by Sparse. Cool. All right, I'll post a link for this, guys, and you can actually work on this, and also kind of play around with this. You can do different metrics, right? You can try different movies. You can change the data if you like. You know what I mean? You can sort of experiment a little bit. Yeah. So it's a pretty straightforward lab. Good, guys. So that's it, right? So look at the Slack, and I will post the link for this. And this is the last lab in our organized labs, what I call them, right? Next one. So start thinking about. So again, as you can see, this is a pretty simple lab, right? Because a lot of the work is done by the packages, and most of the time, we end up doing packages, right? Unless you're writing a custom recommendation algorithm. Most of the time you end up using packages, right? And they will produce, remember this graph, right? They will produce pretty decent results. So remember the saying, right? Where was that? Like Netflix, the Netflix challenge findings, right? Come on. There we go, right? It's like, yeah, it's trivial to kind of do like a pretty decent algorithms recommendations, but it takes a lot of effort to improve on them, right? So we are kind of aiming for the basic run-of-the-mill recommendation. And even with that, we'll get pretty decent accuracies. Yeah. Does that make sense, guys? Any questions? Recommendations? Does it make sense? Right? Good. Sorry, I think Vasily, I couldn't hear you. I don't know if you were saying something.
No, just I was just thinking how I can find out an answer to combining the previous example I was looking for, one hot encoding with the PCA.
Oh yeah, what was the issue? Just show me a link. I didn't have time to. So what was the issue for the errors?
Yeah, it was getting. Was expecting 2 values. I found nothing.
Missing values, right? NAs, right? Yeah. So yeah, definitely, yeah. So kind of either you want to do some basic data cleanup.
You can do it offline. Just if you have any recommendations, how to go around that. Yeah.
Okay. We'll definitely talk about this too. All right, guys. So what else? What else we should talk about? So this is this week, right? Recommendation. Again, like I said, it's a very, very simple lab, right? But I kind of want you guys to start thinking about the project, because that's kind of where you're going to spend a lot of your time the next few weeks. Do you guys have any thoughts on how we should do, right? Any ideas on how we should wrap this up, projects, anything else we want to discuss?
Excuse me, can you explain more about SVD and ASL one more time?
Oh, actually, yeah. So basically, these are these are basically solving matrix, right? So when you have matrices, right, how do you solve these? How do you solve matrices? It's basically what I would recommend, just for the interest of time, if you're really curious, do some quick searches, and you will find, because to kind of understand that you have kind of start from the basic and understand how the matrix is operated, right? So we don't have time right now, so unfortunately, but do some searching around, and you will find some good illustrations. There are some good videos on YouTube that explains how SVD and ALS work, right? So basically, at the point you're looking at, you're solving matrices, right? And these are two different techniques for solving matrices, right? So I'm going to leave it at that, just in interest of time. But if you have any questions, we can definitely talk next week. Yeah.
So what's the main point of use them? Is like PCA?
Yeah, basically, because you kind of want to, right? You want to solve because it's very hard to solve the original matrix, right? Because right, it's very big and very sparse. So basically, you think like PCA, right? Kind of, right? So you break them down to two equivalent matrices, right? To much smaller matrices, much smaller size, and then you solve them. You solve them together, and then you get your answer, right? So rather than solving the one big thing, you're kind of solving two small ones. And how is it possible? Because the way we kind of factorize the matrix is like when you go back, you don't get the original matrix 100%, but you get pretty close to it, at approximate. That's why, right? So you're losing some information when you break them up, right? Yeah. But the reason we are doing this is like this is much more manageable than this one giant matrix. Yeah. So as long as just like PCA, right? And that's why I kind of wanted to do this after the PCA, because when you do the PCA, you realize, yes, I'm never going to go back to 100%. But if I can get, if I can still get the same thing with 90% coverage, but it's much quicker to solve, yeah, I'll take it, right? Yeah. So that's the compromise you're making. Yeah.
It's always two small matrices.
So I mean, these algorithms used to, right? But you can factor the matrix in any number of matrices as you want. But yeah, so in this case too, because we kind of want to maintain the dimension as users and items, see, right? So kind of that's why. Yeah.
Here,
that's why.
Because the original matrix is 2 by 2.
Yeah, it's a two-dimensional matrix, right? Yeah, users on rows and items on columns. And kind of just kind of add to the complexity. I mean, you can also like add other dimensions. For example, you can do like user, and you can also consider things like age, right? Or demography, like what zip code they live in. So you can really make this matrix pretty complex. But as collaborative filtering uses 2 by 2, so 2 by 2, two-dimensional matrix, and that gives you pretty decent results. Yeah, but as you can imagine, you can keep adding dimension to this, right? So for example, users in their 20s will give some same movie for the 20-somethings will give a different rating than 40-somethings, right? You can factor those as well. Then your matrix becomes much more complex. Yeah.
But you said that when you showed us the implementation, you showed ACL, and it comes with which package? It was a skate.
Oh, the ALS algorithm. Yeah. So this is a generic algorithm. So which is implemented by pretty much all the machine learning libraries, right? So there are basically two approaches. I mean, again, at least the two sort of we look at SVD. SVD is kind of very intensive computationally. So ALS is kind of a shortcut. It takes some approximations, and but it gives you pretty close results. That's why a lot of the algorithm implement ALS, right? Because computational is much more efficient. That's why. Yeah. So. Oh, cool. Yeah. Very good. Thank you. So, all right, guys. So next week we will look at the solutions for this one, and we will finalize the project. Anything else, guys? Anything else we should discuss? Also, next week, I also need some help from you guys. I want to get some feedback from you guys on the on the program, and what worked well, what we need to improve, because this is kind of the first time I did something like this, right? Kind of like a more like a weekly series kind of a thing, right? So I know initially we had some issues with all the different tools and everything. So I kind of want to get your input, right? And then I really value your input, because you guys have went through this, you guys submitted, you get stuck with the program for months on end, right? So I really want to kind of see if you want to do another series, how what we can improve on, right? So I'll send you guys like a little like a survey kind of a thing. So feel free to tell me your answer, right? You can be candid, and also I want to discuss this next week as well, right? Because I want to see your input, and I want to make sure, because you are spending your time, right? And I value that. So we want to make sure, like, if we want to, so you guys are the first batch. So you guys kind of endured some of the issues we had to, the first being as the first, right? First ones. So if you want to do another batch, right? How can we do, more efficiently, things like that. So anyway, so I'll send out a survey, and then you can give me some answers, and I really look forward to your recommendation as well. Good, guys. So get busy thinking about your project, right? Because that's the fun. And remember, you're doing the project for you, right? Kind of like you're gonna showcase to other people, right? Your employers and things like that, right? So think about and I recommend combine your domain. Let's say you work in finance. I'm just making this up, right? Let's say you work in finance. You probably want to find a data set that's more finance oriented, because then you understand it, right?
Mhm.
And it's relevant to your experience, right? And then you can say, oh, I don't know, I found this finance data set, and this is my machine learning I did, and this is what I discovered. So
Mhm.
that'll really help you, because I'll tell you this: people who do well in machine learning, like career-wise, are not like generic. Like it's not like okay, I can do machine learning on any domain. You want to combine your domain skills. Let's say you work in healthcare, right? So you know how the what the data looks like. You want to combine your domain skills and machine learning, and that'll make you very unique, right? Yeah. So keep that in mind. We will discuss more next week. Yeah.
But thank you so much. Since I came at the kind of tail end, I would be interested in starting at the top if you can provide another series.
Gotcha. Yeah. So we are all going to take some time off, right? Because yeah, there's and again, I know you guys were like my sort of troopers. You guys were like the first batch. So we kind of did a lot of experimentation, but I think we kind of eventually figured out kind of found like what works and what doesn't. Yeah. So and that's why I want to hear from you guys, right? And then yeah, we'll definitely do another series, and I'll take some time off, and I will come back and launch another series. And even you guys, like if, for example, what would be another series for you guys look like, right? So I already had some requests from you guys. Some of you approached me about for deep learning series like this, like we did machine learning now. Can you do deep learning? And can you do more like NLP stuff, natural language processing, right? There are a lot of specialized track we can do. So yeah, so we can talk about this too then the next week, right? Good. Cool. Thank you, guys. So that's all this week. Anything else?
What is supposed that we do next week together?
So next week you're going to do the recommendations lab, right? And that's the final algorithm we are going to cover, right? So collaborative fluent recommendations. And then next week, let's also talk about and kick off the final project, right? What you guys have learned a lot of algorithms, right? So let's kind of figure out, okay, we want to do a final project that kind of showcase all your learning, kind of put all your learning to use. Yeah. And we'll talk more. And I'll send out a survey, and I'll have you guys fill it out, and we'll discuss more, right? So we'll launch our final project by next week. All right, guys, very good. Thank you so much. I will see you guys next week, same time, yeah? Okay.
Thank you.